All right, so in the previous lesson with law of sines, we talked about how every now and then you're solving for an angle in an oblique triangle and you end up with more than one possible angle. And that's because of this topic here called the ambiguous nature of sine. The law of sines is known as ambiguous because it doesn't always result in a unique solution. We could have zero solutions, we could have one solution, we could have multiple solutions. Now, if we have a side-side angle triangle, that's typically when we see this happening, because it's possible to get more than one version of that triangle with that given information. If I have a side-side angle triangle like what you see here in the top margin, this is only going to have one solution because that 14 is too long to slide anywhere else, right? So if the opposite side from the angle is longer than the side adjacent to it in an SSA, labeling system, you're going to have just the one answer. So that's not the ambiguous case. The ambiguous case is something like this, where you see this side across from the angle being shorter than the one next to it, because then that 6 can swing back this way, and it's possible to create a triangle that has the obtuse angle at C rather than at A. And so we need to find all the possible values for C, and that's going to be going to require a couple extra steps. So let's go through this situation in which we have a shorter opposite side than we do an adjacent side. All right, so in this case, let's say we're solving for angle C. I'm going to put a theta here. All right, and that theta will connect across to the 10. The 36 connects across to the 6. Okay, so we say that sine of theta over its opposite side 10 is equal to sine of 36 over its opposite side 6. So when I go through the whole cross multiplication, inverse sine, theta is going to equal inverse sine of this 10 sine 36 over what I would have divided by on this diagonal, which is 6. And so that comes out to approximately 78.4 degrees. So one of the possible answers for theta is 78.4. Now, I have to check it with its partner here, because it's possible that it's the obtuse version. So if I do 180 minus 78.4, I get 101.6. And the larger version, 101.6, would work as well, because with this 36-degree angle, I would still have enough degrees remaining for angle A. So there actually are two solutions to this triangle. All right, now sine is ambiguous because it's positive for all angles on the interval from 0 to 180. You'll get more on that in pre-calculus. I don't want to get too far into that now. But in most sine equations, two values will be possible. You get an acute version and an obtuse version. But once in a while, we'll get a situation where we don't get two solutions. So let's go through one of those. So here's one where that opposite side is longer than the adjacent side. So if I go through that, I'm thinking I'm only going to get one solution because that 14 isn't going to be able to slide to another position. But let's go through this. So angle B gets my theta, go across and across. And so I have sine theta over 10 equals sine 80 over 14. All right, well, 14 sine theta, 10 sine 80. When I do my inverse sine, theta is inverse sine of 10 sine 80 over 14. And that comes out to 44.7 degrees. So if I take the obtuse version of that, it would be 135.3. Now, if I take 135.3 and I add it to 80, I'm already well over 180 degrees. So that's a scenario where the second angle is unrealistic. So I just disregard it, and 44.7 is the only answer for angle B. And as I suspected, because that 14 doesn't have room to swing anywhere. So there's an example of just one answer. So considering the measures, the angles of any triangle must sum to 180. Why must we reject that obtuse solution? Well, if I take that 135.3 and I add the 80 degrees, I'm at 215.3, and we're not allowed to exceed 180. Okay, so exercise 3, explain why the triangle shown below cannot exist by finding all possible values for angle C. All right, well, let's go through this one. So angle C gets the theta. I go across and across, and I have sine theta over 18 is equal to sine 52 over 12. And so sine theta comes out to 18 sine 52 over 12. All right, so then my theta must equal the inverse sine of that ratio, 18 sine 52 over 12. Well, when I do this on a calculator, if I type 18 sine 52, it comes out greater than 12. And that doesn't make any sense here because remember, the sine ratio, this is inverse sine, by the way, sine ratio is supposed to be opposite over hypotenuse, right? So if it's opposite over hypotenuse and the opposite side is bigger than the hypotenuse side, it's not going to work. That's a triangle that never existed. So if you were to type this into your calculator, if you tried it already, you probably got an error message, and that's because the numerator can't be bigger than the denominator in an inverse sine or an inverse cosine equation. So that's why this triangle doesn't exist. So there's a scenario where the opposite side was smaller than the adjacent side, and we got no solution. Sometimes we get no solution, sometimes we get two solutions. And sometimes when that opposite side is shorter, when that opposite side is longer, like in exercise, where am I here? In exercise 2A, that's when we get just the one solution. All right, so let's go on to exercise 4. In triangle DEF, angle D is 72, and DE is 12, and DF is 15. So let's just quick draw that. So I get my triangle, we'll call this angle E, 72 degrees. All right, so this could be D, call that 12, this could be F, and call that 15. Okay, how many triangles are, oh wait, DF is 15, not EF. So let's fix that. So DF is 15. Okay, how many triangles are possible given this information? Well, if we run through this, because that opposite side is longer, I'm pretty sure it's just going to be 1. But let's just check it one more time. So I have sine 72 over 15 equals, and this is angle, let's call this angle F theta, sine theta over 12. All right. So my theta in this case is going to be the inverse sine of 12 sine 72 over 15. And if I solve that, I get 49.5 or 130.5. And this is very similar to the one on the previous page. That 130.5 is too many degrees for 72. So I discard that. I get the one answer, which means there was exactly one triangle. All right. So from this point forward, if I have an SSA and the side across from the angle, we'll call that side 2 and call this side 1. If side 2 is greater than side 1, then that means we're going to have one solution. If side 2 is less than side 1, that's the kind where it can swing in. And so in that case, we could have two solutions or we could have zero solutions. Those are the two possibilities there. So this is what we're dealing with ambiguous case. You got to look at that side across from the angle and see how it relates to the other one next to the angle. All right, exercise 5, we've got a triangle ABC. And angle A is 60. I've got a 10, got a 10 root 3. And we want to figure out something about angle B. Okay, so let's go through this. Angle B, if I were to set this up as sine 60 over 10 root 3 equals, let's put the theta here. You know what, I have to put the theta at C, only because angle B doesn't have a side across from it. So I'd have two variables if I did law of sines with angle B. So I'm going to do it with angle C. Once I solve angle C, I can go back and get B. All right, so if I work on this, sine theta over 10, and then theta would equal inverse sine of 10 sine 60 over 10 root 3. And so theta comes out to 30 or 150. Well, that 150 is too many degrees for 60, so theta equals 30, which means angle B must be 90. Now, wait a minute. This was a right triangle. Okay, well, let's think about that for a second. That kind of makes sense here, because if you look at the 10 and the 10 root 3, we know something about sides that are related that way. 10 times root 3 to get to 10 root 3. In a 60-degree triangle, it was pretty likely that angle B was a right angle. So that actually makes sense using our right triangle strategies, but the law of sines showed us that this angle C had to be 30, couldn't be 150, so angle B must be a right angle only. So this is choice 3. Okay, exercise 6. We've got triangle CDE, and that's already drawn for us. That's nice. All right, so let's go through this. I've got, I'm trying to figure out all areas for CDE. Now, area requires us to use an angle with two known sides surrounding it. So I think this is the angle that I want. If I can figure out angle C, I can use that in the area formula with 13 and 18. So let's work on that. Let's say I go sine 40 over 13. Now here I'm stuck, right? Because if I want to use theta, I don't have a side across from it to use. So I'm going to have to figure out this angle first, angle D, we'll call it alpha. It's the second variable for angles. So I go sine alpha over 18. So alpha will equal inverse sine of, let's see, 18 sine 40 over 13, which equals 63 degrees, or possibly 117. And just checking that obtuse angle, it actually does work, which I would think it would, since 13 is shorter than 18. 117 with 40 still leaves me some degrees here. So I've got to calculate this both ways now. So let's say if angle D is 63 degrees, then angle C is 77 degrees, right? If this is 63, 63 plus 40 is 103, angle C would be 77. So in that case, the area would be 1/2 13 times 18 times sine 77. So that solves out to about 114 square inches. And if angle D was not 63, let's say if angle D was 117, then angle C would be 23 degrees. So the area formula would change. It would be 1/2 13 times 18 times sine 23. And that area comes out to a smaller number. It comes out to 46 this time. So it's possible to get two different areas because, again, that 13 could have gone this way. And if it did, it's clearly a smaller triangle. So that's why we get two answers to that. All right, let's finish this up. Exercise 7. So it is known that PR is 10, I got that, and that angle Q is 30. Find all the possible values of R such that the two measures are possible. All right, well, let's, since I have a little R here, let's put a theta here, and let's use law of sines here, and see what we come up with. So I've got sine theta over R is equal to sine 30 over 10. Now this wanted us to think in terms of possibilities for R. So if I were to think about this as sine theta, let's just quick multiply both sides by R here and get sine theta by itself. So sine theta would equal R sine 30 divided by 10, right? It's this diagonal divided by 10. So such that these two measures are possible. All right, so that means what could I have where the triangle exists? Well, if I'm looking at sine theta equals this ratio, because of sine being opposite over hypotenuse, then I know that that R sine 30 has to be less than 10. Because if it's equal to 10, I don't have a triangle. If it's more than 10, I don't have a triangle. Has to be less than 10. So that R value has to be less than 10 divided by sine 30. 10 divided by sine 30, if you just put that into your calculator, that comes out to 20. So R must be less than 20, but I can't just leave it like that because R has to be something positive. So 0 between R, or R between 0 and 20, it wants interval notation. So that would be from 0 to 20 written as an interval. All right, so lots of applications of law of signs here in the ambiguous case.